Before I go through my presentation, I'm hoping that everyone, most of you, know about permutations and derangements, but I'm going to say something about permutations. Permutations are arrangements of objects. If the objects are a set of natural numbers from 1 up to some positive integer n, then we can take it as a bijection between this set to itself. And a derangement is a special kind of permutations, but no element appears in its original position. So when I come to my presentation, we have studied this particular kind of permutations, which are called parity alternating permutations. Parity alternating permutations first introduced by a Japanese mathematician called Tanimoto, which is the even and the odd integers alternatively. But the one we are studying currently now are the Tanimoto's permutations that started with an odd integer. We call them PABs in short. So when we say this permutation start with an odd integer, that indicates as always the odd positions are in the odd position there are only odd integers, and in the even position there are only even integers. So this helps us to see some splitting method or some splitting way of these PABs into two words. For example, I have two examples here. If I have this permutation, if you see 5, 2, 1, 4, 3, 6, 7, the next one is a cycle representation of the permutation. And we can split this one into two subwords, since all the odd positions are occupied by the odd integers and all the even positions are occupied by the even integers. So when we take out the odd ones, we have 5, 1, 3, 7, and its cycle representation, and 2, 4, 6, and its cycle representation. And by the way, the cycle, if we consider the cycle representation, the splitting method shows us or allow us to see the cycles containing the odd integers and the cycles containing the even integers are completely disjoint. So these separated subwords are actually, we can relate them with bijectively with, for example, 5, 1, 3 is correspond with 3, 1, 2, which is a permutation over 4, and 2, 4, 6 is correspond to 1, 2, 3, which is a permutation over 3. And similarly, we have this one. So this method, we actually start finding our results by applying this method, and the consequences, I'm going to present here the consequence of this method or the splitting PABs. One example of a consequence is counting the number of PABs that will be found with this formula, because we can count the integers which appears on the odd position and the integers which appears on the even position. Here we denote a small pn to say the number of PABs over n, where the capital Pn indicates the set of PABs over n. So here we have a sequence that counts these PABs. Actually, this sequence appears online. That means in the online encyclopedia of integer sequences, but they count many different things. And the other consequence of this splitting method is a recurrence relation over here with defined with a given initial condition P0. So this sequence this sequence appears in the online encyclopedia of integer sequences with this number, and also it has an exponential generating function over there, which is found by Paul Dihana. But since there is no proof, documented proof, we give constructive proof for this exponential generating function. The other way we try to see this parity alternating permutations by considering the parity of them. While we are saying parity of a permutation, we mean by parity of a number of inversions of the permutation, or the parity of the number of cycles in the product of transpositions of the permutations. So we try to give a notation for the set of all even permutations. That means when we talk about a parity, either we say even or odd. So the set of all even permutations by this and the set of odd permutations by this, and their cardinalities denoted by PEN and PON. So surprisingly, they have actually almost similar, these two numbers, after n greater than or equals to 3. So this is two sequences we already introduced. So when we see this, after n greater than or equals to 3, we see the equality of the two numbers. So these two numbers are also satisfying these two recurrence relations, and also they have exponential generating function determined by P of x. P of x is the exponential generating function that we talked about earlier. So in try to summarizing the relation or the comparison of permutations and PUFs, here we have sequences which express the number of permutations and the number of PUFs over here, and the EGF, which is the exponential generating function for the permutations, is this one, while this is for the exponential generating function for the numbers that count PUFs. So distinguishing them with their parity, we have these two sequences, and for the permutations, and these two sequences for the PUFs, and their exponential generating function are compared like this. So the other specific kind of these parity alternating permutations or PUFs are called parity alternating derangements, which are the PUFs which are also derangements. The PUFs that we were talking about, and which are also derangement. That means derangement starting with an odd integer. So the splitting method that we are we were looking is also applying over here, and we give some result of the consequence of this splitting method on the parts also. So one is counting these numbers, or counting the number of parts over n in terms of the number of derangements, because when we split, we get two derangements. So in that case, we can find the number of parts by the number of derangements in this way, where dn indicates the number of derangements, but the Gothic dn indicates the number of parts. Here we have the first few values of the dn and the Gothic dn. And also the other result that we have found is a recurrence relation for this number of parts. Here it is expressed in here, where S is a number that's written over here, which is the floor n minus 1 over 2. And also these numbers also satisfy another recurrence relation in terms of the number of parts and also the number of derangements, where S is this number with initial conditions, this one. And if we apply, or if we try to distinguish these parts into two ways, or applying the parity, and we can determine some sequences over here where we denote the number of even parts and the number of odd parts by this one, but the number of even and odd derangements already been studied by many mathematicians, in particular Roberto Mantacci and Fanjara Kotundrajao. So we try to apply these studies and try to find some results on these numbers. So the first result is finding or giving a formula for these two numbers, the numbers that count the even parts and the numbers that count the odd parts, in terms of the numbers that count the even and the odd derangements in this way. And also the corollary is which we can see that we have these two numbers satisfy this two recurrence relation, where S is this number and given initial conditions also. So we also try to see the difference of these two numbers. That means if we take the difference of the numbers that count the even parts and the numbers that count the odd parts, we get this formula. And we have given a bijective proof for this one, and we distinguish what kind of parts give or counted by this Fn or counted by this difference. So we have over here the sequence. It's actually an alternative version of the sequence on the online with this one, which has an exponential generating function introduced by Paul Barry, but he introduced it using Mathematica, so we gave a constructive proof for the exponential generating function. So we also studied these pads and statistical distribution statistics called excedance. And an excedance of a permutation is when we say a permutation sigma has an excedance on I if sigma of I is greater than I, and we give these notations which are the pads, the number of pads over n having particular k excedance, and depending on their parity we have given this. So as I was saying, Mantachi and Rakoton Rajao were give a deep study on this kind of, I mean, the numbers of the derangements with excedance distribution, having an excedance distribution. So we use this one to see some result for these numbers. So these numbers satisfy the symmetric properties. Here we have over here, and these are the data we have. That means the sequences in table form. So when we try to see them, they satisfy symmetric properties. And also we can find this one, this excedance distribution for a parts by similarly applying the splitting method. We can determine, or we can find, or we can use this formula to determine the numbers of pads over n having k exceedances depending on the number of derangements with particular exceedance value or exceedance number. So if we take also the parity on this exceedance distribution on pads, we also have this a little bit long, but this formula which also depend on the derangement numbers. So we also take here the difference of the two numbers. That means the difference of the even parts over n having k exceedance minus the number of parts having over n, the odd parts over n having k exceedance. We distinguish this formula, which is we proved it with a recursive way, or we use a recursive proof to show this one is correct. But now we are currently working on a bijective proof for this one and trying to determine what kind of parts are counted by this FNK or these differences. So here we have a table to indicate the difference, and also an exponential generating function for this difference. So as a summary, we have a comparison table between the derangements and the paths. Here we have the sequences that counts the derangements and also the paths and their exponential generating function. But for us, we don't actually get it till now, the exponential generating function for the sequence, this one, or that counts the paths, which is still open. And also, if you see the recurrence relation, it's already known. This is a famous, actually, these two are famous recurrence relation for the number of derangements. Also, we have, which is connected to these two recurrence relation, we have for the numbers that count for the paths, which we already introduced here. Also, if we consider the parity, we have these two sequences for the derangements and also for the paths. And as we see here, we have for the exponential generating function for the derangements with their parity, but for us it is still open. But for their recurrence relation, we already have it over here. And also, if you take the difference between the even and the odd ones for the derangements, we have over here, and which contains the excedance, the difference between the derangements, the even and the odd derangements with excedance distribution, we have over here. Also for the paths, we already found formula 5 and formula 6. So this is for we try to compare derangements and paths, but there are also some open problems that we didn't solve yet. So these results are applied, like we apply all splitting method to find those results, but this splitting way or the splitting method is not always applicable on paths. For example, if we take the pattern avoidance over paths, if we consider a pattern P, which is 1, 2, and if we try to see the numbers or the paths avoiding the pattern P, for example, if you consider the derangements, or actually the only derangements that avoid this pattern P is the decreasing arrangement or the decreasing derangement, which is, for example, if n is 4, we take 4, 3, 2, 1, that it avoids P. However, if we take this pad 7, 8, 5, 6, 3, 4, 1, 2, and try to apply a splitting method, we have the odd integers 7, 5, 3, 1, and for the even integers 8, 6, 4, 2, and they bijectively written to one derangement, which is 4, 3, 2, 1. Both this actually it is the same, avoids P. However, if we try to see the original or the pad, which does not avoid P, it actually contains P. So that we try to show here our method that we use is not applicable all the time. That one example is pattern avoidance. And our next project is looking or counting the numbers or see the behaviors of the number of paths or pubs that avoid a particular P, mostly the patterns with length 3. So that's our next project that we plan to work on. And I have a very short presentation. I think I have finished my presentation. So that was it. This is the references that I used here for the presentation.